In this video, we're going to talk about binomial and geometric random variables. First up, let's talk about something called a binomial setting. So that arises when we perform some n number of independent trials of the same chance process and count the number of times that a particular outcome occurs, and we call that particular outcome a success. So there are 4 conditions that a binomial setting must meet, and the cute little acronym is BINS. B-I-N-S. So the first one is it binary, which means the possible outcomes for each trial can be classified as either a success or failure, a binary, 1 or 0. Next, is it independent? Trials must be independent. That is, knowing the outcome of one must not tell us anything about the outcome of another. The third setting is number. The number of trials n of the chance process must be fixed in advance. And lastly, S stands for same probability. There is the same probability of success P on each trial. So all 4 things must be met in order for it to be a binomial setting. So let's look at 2 examples where we might identify a binomial setting. So first up, we have genetics say that the genes children receive from their parents are independent from one child to another. You've probably learned that in biology. So each child of a particular set of parents has the probability of 0.25 or 1/4 chance of having type O blood. Suppose these parents have 5 children. Count the number of children with type O blood. So let's check the bins on this scenario to see if it is a binomial setting. So first up, is it binary? So I would say that having type O blood in this scenario is quote unquote a success, and not having type O blood is a quote unquote failure. So that is binary, yes or no. Independent? Well, knowing one child's blood type doesn't tell you anything about the other kid's blood types because they are independent of one another. So 2 for 2. And then the number, that's going to indicate the number of trials or the number of kids in this setting, and that is 5. And do they all have the same probability of occurring? Meaning, do they all have the same chance of success or having type O blood? And that is also true. That probability is 0.25 or 1 out of 4. So yes, it meets BINS, so it is a binomial setting. Our second example says to shuffle a standard deck of 52 playing cards. Turn over the first 10 cards one at a time and record the number of aces you observe. So let's check in on BINS to see if this is a binomial setting. So checking B in BINS is it binary? So I would say getting an ace is a success and not getting an ace is a failure. So that is binary. It's a yes or no. Is it independent? It's not. So if the first card you turn over is an ace, then the next card is less likely to be an ace because you're not replacing the card you draw back into the deck. And if the first card isn't an ace, that means the second card is more likely to be an ace than the first. So pulling cards out of a deck like this is not independent because those odds are dependent on one another. So unfortunately, this is not a binomial setting. So if we have a binomial setting, so it meets all 4 criteria of BINS, that means that we have a binomial random variable for all those successes that we might call X. So we know a lot about random variables already. So if it meets a binomial setting, it's a binomial random variable, and so we know that random variables also have a binomial distribution. That is a probability distribution that is specified by 2 numbers. The number of trials n of the chance process and the probability p of the success of each trial. So one important piece of that is something called a binomial coefficient. So that is the number of ways to arrange k successes among n trials, and that's given by this thing here. So you may have seen this as a probability combination before, and it has this equation. Essentially, if you know however many trials you have, you do n factorial. So if it was 4, you do 4 times 3 times 2 times 1, because that's what a factorial is. And then you would calculate the numerator, or k, as k, so that is the number of successes factorial, times the difference of n minus k factorial. And that is the definition of combination in probability. So, for example, this is 5, choose 2. That's another way of saying combination. So that is 5 factorial on the top k or 2 factorial on the bottom, and then 5 minus 2 is 3 factorial, and you just do the thing. Now, I'm going to show you a couple other ways to think about this or to work this out depending on what you prefer. So if you like this definition, great. And if that's not so great for you, a second option is something we call Pascal's triangle. So you may have seen this before. It is a pattern of numbers using a triangle shape and addition. And so each row has an n value, and within that row is our k value, which I'll get to in a moment. But how do you build Pascal's triangle? You don't have to memorize it, as long as you remember that you start with 1 on the top and you do 1 and 1 the next row down. Notice that this has 1 number, this has 2, that has 3, etc. You add 1 each time you go. And speaking of adding, in order to figure out how is that 2, well, if you start with 1 and 1 and 1, and also notice that 1s are going to be on the outside of your triangle all the way down. So 1 plus 1 makes 2. And then how do you figure out these two numbers here? Well, 1 plus 2 makes 3. 2 plus 1 makes 3. 1 plus 3 makes 4. 3 plus 3 makes 6, etc. And so every row is an n value starting at 0, because anything to the 0 power is 1. And then if this is n equals 1, these are your 2 coefficients. N equals 2, these are your 3 coefficients, etc. And so if I took a look at n equals 3, you're going to have 4 different coefficients. And then our k value is each value in order in that row. So if your first number is 1, which it should always be, that's going to be k equals 0. And the next number is k equals 1, etc. So that's how you use Pascal's triangle to help you with binomial coefficients. And if you're a patterns person and you just like drawing random number triangles, this one might be great for you. But if either of those don't really strike a chord for you, you can always use your calculator. So this is the third way to do that. And like I was saying, we are talking about a combination in mathematics or in probability. So what essentially you're finding is you have 5 things to choose from, and you're choosing 2 of those 5 things. How many different ways can you do that? And C, if you think back to like middle school mathematics, there was always P and C. P stands for permutation, C stands for combination. P is where order matters, and C is where order doesn't matter. So the order doesn't matter here, if that helps remembering what to use. So you can find the math menu, and then you page over to the probability menu, and then you pick NCR. But before you do that, before you even go into this menu, I should have mentioned, whatever number you want to put first, so if you are choosing from 5, then you need to type that number first. You'll figure that out if you go into the menu and you aren't allowed to type something there. You'll figure it out. Your fancy newer calculators might have these little boxes open for you to just type into, which is really great. And so you type 5, you find this in the math probability menu, and then you type 2, however many you're choosing, and that's going to give you your coefficient, which is a heck of a lot better than doing this. Maybe better than Pascal's triangle. That's up to you. So that's a third way to find binomial coefficients. Now you may be thinking, cool, a binomial coefficient, but don't coefficients usually go in front of something? And you'd be right. So they go in front of something called the binomial probability formula. And that says, suppose that X is a binomial random variable, passes the Bin's test, with n number of trials and a probability P of success on each trial. Remember, it has to be the same each trial. The probability of getting exactly k number of successes in those n trials, where k starts at 0, 1, 2, etc., is this equation. So it is the probability of X, so our binomial random variable, equaling our k number of successes that we're trying to find. So this thing in parentheses, n over k, that is our binomial coefficient that I just showed you 3 different ways to find. And then you multiply that by P, so the probability of success, to the K, so however many successes, times 1 minus P, that probability, to the n minus K exponent. Super fun. So many variables. Obviously, let's take a look at an example, and let's again talk about inheriting blood type. So genetics say that genes children receive from their parents are independent from one child to another. Each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose these parents have 5 kids. Let X equal the number of children with type O blood. Let us find the probability of X equals 3. So achieving 3 kids out of 5 with a type O blood type. All right, so I'm going to use this equation that we saw on the last page. And so we're looking for px equals 3. And so that's 5, choose 3. The probability is 0.25 to the third power because that's the k value we're looking for. And then 1 minus that probability, 1 minus 0.25, n minus k, 5 minus 3. 5, choose 3 of whatever method you prefer, ends up being 10. So that is the binomial coefficient we're talking about. Then we just simplify these guys here and we get that there's about a 9% chance that exactly 3 of those 5 children will have type O blood. So what if we wanted to find cumulative binomial probability, meaning the probability of more than one thing happening? So let's take that type O blood example that we've been using. Should the parents be surprised if more than 3 of their children have type O blood? Let's calculate an appropriate probability to support our answer. So we take the same formula that we used in the last example. And so this time we're looking for the probability of x being greater than 3. So all we got to do is find the probability of x being 4 and add it to the probability of x being 5. So I work out all of this math and I end up with a 0.01563 probability. So should the parents be surprised? Absolutely, because the probability is about 1.5-ish% of having more than 3 kids, or aka 4 or 5 kids with type O blood. They should be very surprised if that happens. And very fortunate, depending on if they're O neg or O positive. They can all just like donate and receive from each other, right? I don't know, ask your bio teacher. But something you shouldn't be surprised about is that you can calculate binomial probabilities using your calculator. So let's say we wanted to find the same thing in the first example where they wanted to know exactly if 3 kids would have type O blood. So that is probability where x equals 3. So you would press second vars to the distribution list and you would choose something called binom PDF. So that is when you want the exact number. So you enter in your n value after the parentheses. So that would be 5 because there's 5 kids. P is the probability, which is 0.25. And K is the number that we're looking for, which is 3. And for the second part of that question, where they were wondering if 4 or 5 of their kids, or the probability of 4 or 5 of their kids have type O blood, you have to do a little more arithmetic here. So there is also in that menu, there's binom CDF, and that computes, instead of x equals that particular number of successes, it's x is less than or equal to that particular number of successes. So remember, we were looking for technically 1 minus x is greater than or equal to 3. So that would have been 4 or 5. And so what we end up doing is we'll take this binomial CDF and we'll subtract it from 1. So when you use binomial CDF, you still put in the n, the p, and the k. And so you would put in 5, 0.25, and 3 into the CDF. And that will give you about 98% right here. And so if you do 1 minus that value, that's where we get our about 1.5% there on the bottom. Alternatively, you could have done binomial PDF of 4 separately from 5 and added those 2 values together, and you'd still get the answer we got there. And if you wanted to look at a histogram of your probability distribution for that problem with 5 kids and their type O blood, you would enter into a list where we've typed many a list before. And so you'd have 0 through 5, right? Because 0 kids with type O blood all the way up to 5 kids with type O blood. Now, you don't even need to calculate those because your calculator can do that for you. And so if you highlight L2 with your cursor on your calculator and you enter that command, binomial PDF of your 5 and 0.25, and you hit enter, it will populate that list for you. Isn't that beautiful? I love it. And then you can also graph it as a histogram if you wanted to look at the shape or the variability or any other type of visual needs you have. Your calculator can do that as well. So just like with regular old random variables, binomial random variables and their probability distributions have means and standard deviations. So how do you find the mean of a binomial random variable probability distribution? That is a mouthful. All you really got to do is you take the number of trials, n, and multiply it by the probability of success, p, and that's your mean. Real difficult. And the standard deviation is going to be the square root of n times p, so the number of trials times the probability of each, times the 1 minus p value. Now, obviously keep in mind that these two equations, the mean and standard deviation, they only work for binomial distributions. So a quick note on sample size. Now, there's something that we call the 10% condition, and that is when our sample size, so lowercase n, of a bigger population, so uppercase n, has to pass something called the 10% condition. So in practice, the binomial distribution gives a good approximation of that entire population as long as we sample less than 10% of that population. So as long as our lowercase n, the sample size we're working with, is less than 0.10 of that population. And so another thing to keep in mind in terms of lowercase n, or our sample size, when n is large, and it's still 10% of that larger population, so we're probably talking about a big population. So when n is large, we can use normal probability calculations to approximate binomial probabilities. And so if you want to check if your n, your lowercase n, is large enough, we have to check something called the large counts condition. So again, x is our number of successes, that is our binomial random variable, and it has a binomial distribution with n number of trials and p success probability. The condition says that the probability is approximately normal if your number of trials times your success probability multiplied together is greater than or equal to 10. And the number of trials with the probability of failures, right, 1 minus p, if p is success, is also greater than or equal to 10. And this visual gets to this large counts condition in terms of normal distributions. So if you have the same probability in all three, they're all 0.8 or 80%. If you start with n equals 10, so a number of trials is 10, you get this distribution. Looks kind of normal, but it gets far more quote unquote normal, with capital N, right, because statistics. We increase from 10 to 20, it's starting to get way more normal. And then from 20 to 50, it's really, really obviously very normal. It's got a really beautiful bell curve, and we can apply all those normal probability calculations and procedures to those things if n is great enough. So keep in mind the 10% condition and the large counts condition. So we've been talking about binomial probability distributions where the number of trials, or lowercase n, is fixed, and then we're trying to count the number of successes, or k. So the opposite, where we know the number of successes, that is fixed, and then we go looking for the number of trials, or n, needed to find that desired number of successes. That is called a geometric setting. So that's when you perform independent trials, same chance process, and then you record the number of trials it takes to get one success. So on each trial, again, the probability p of success must be the same. So here are three examples. Let's say you roll a dice until you get doubles. And in basketball, you attempt a 3-point shot until you make one. And you keep placing a dollar bet on the number 15 in roulette until you win. And so if this is a geometric setting, just like a binomial setting, it's gonna have a geometric random variable and a corresponding geometric probability distribution. It works just the same, but instead of x, we're going to use y. And of course, the equations to find different things about geometric settings and their variables and distributions is slightly different, but we work with the same kind of values. So of course there's a geometric probability formula, and that says if y has a geometric distribution with a probability p of success on each trial, the possible values of y are 1, 2, 3, etc. And if k is any one of those values, then we calculate the probability of y is equal to k is 1 minus that probability, so essentially that not happening, to the power of k minus 1, whatever it is that we're looking for, times that probability. And then the mean is so easy. All we gotta do is take the expected value, which is the mean of y. We take the probability and we do 1 divided by that probability, and that is the mean of a geometric random variable. All right, let's check out one example about geometric distributions. So suppose you roll a pair of fair 6-sided dice until you get doubles. So that's how we know it's a geometric distribution, and let's capital T equal the number of rolls it takes until you get those doubles. So note that the probability of getting doubles on any roll is 6 out of 36, or 1 out of 6. So first up, let's show that T is a geometric random variable. So we know that dice rolls are independent, and the probability of getting doubles is the same on each roll, which is 1/6, and we are repeating the chance process until we get success, or doubles. So this is a geometric setting, and T is a geometric random variable with a probability of 1/6. So next, let's find the probability that T, or the number of rolls it takes to get doubles, is 3. And of course, we'll interpret the result. So we take our probability formula, and we plug in T for Y and 3 for K, because that is what we're asked to do. So 1 minus the probability is 1 minus 1/6. K minus 1 is 3 minus 1 times the probability, which is 1/6, and we get approximately 0.1157, which is the following. Probability is about 11.57% that you will get the first set of doubles on the third roll, or our K value, of the dice. One last thing, I promise, and that is how to calculate geometric probabilities on your graphing calculator, which is very useful. So that same list as the binomial, which is second, vars, and then the dist list, you would choose the geomet, either PDF or CDF. And so much like the binomial, the PDF P comma K computes that Y value is equal to K. So for example, if your p-value, your probability is 1/7, and your x or your k value is 10, all you got to do is put in geomet PDF 1/7, comma 10, and that's your probability. And CDF works very similarly to the binomial one, where instead of it being y equals k, we've got y is less than or equal to k. So let's say you wanted to find the probability of y being less than 10. So to find that using the geomet CDF command, you would really want p is less than 10, but p where y is less than or greater than 9. So you would plug in 9 into the geomet CDF, and then you calculate that value that way. So play around with it, try it out or not, up to you. All right, a big old hip hip hooray that this video is finally over, and thank you for watching.